Hi everyone, in this video, I would like to share my research on stochastic approximation approaches for discrete time nonlinear stochastic optimal control problem in engineering applications. There are 5 parts in this video: introduction, literature review, methodology, result and discussion, and the conclusion and recommendations. First, let's start with introduction. The optimal control theory is a branch of applied mathematics uses mathematical optimization techniques to determine a set of control variables for minimizing the performance index over a dynamic system. A control problem consists of a function in terms of the state and control variables known as a cost function and a dynamic system that is a class of first-order differential equations. The goal of the problem is to optimize the cost function for which the system evolution is towards stabilization. A discrete time system is a signal processing entity that processes the discrete time signal, where the discrete time is referred to the time in a set of integer numbers. A system is considered nonlinear if it does not obey the superposition principle, which means its output is not strictly proportional to its input. In the real world, most systems are nonlinear and are more difficult to analyze as they cannot be decomposed and solved independently. In the presence of random noise, the fluctuation behavior arising will lead the dynamical system to an undesired solution. The problem in such a stochastic dynamic system is commonly known as the stochastic optimal control problem. In engineering applications, optimal control ensures a strategic approach to increase productivity, and it helps to minimize the redundant manual controls that could expend a large amount of money. It also compensates for disturbance, allowing the system in engineering to produce the correct output even in the presence of disturbance. Therefore, the formulation of a mathematical model for studying stochastic systems is very crucial for control and decision-making problems in engineering. Stochastic optimal control deals with the existence of uncertainty in the observation and the randomness of noise disturbance in the dynamic system. The random noise affects the evolution of dynamic system and the observation of the state variables. The state estimation is an important step in handling the stochastic dynamical system. The KF approach provides the optimal state estimate for the linear dynamic system, while the EKF approach is the common method used for estimating the state for nonlinear dynamic system. The state estimation problem can be defined as a stochastic optimization problem over the stochastic dynamic system. The aim is to obtain the optimal state estimate, and thus the optimal control law can be designed to minimize the performance index of a dynamic system. The stochastic approximation (SA) approach, which is also known as the stochastic gradient descent (SGD) method. It is an efficient method for solving stochastic optimization problems. Recently, the SA approach has been the central efficient and effective optimization method in the machine learning approach. Nevertheless, the applicability of the SA approach in handling stochastic optimal control problems shall be further investigated. Moreover, some recent variants of the SA approach are further investigated. The stochastic approximation with momentum (SAM) replaces the current gradient with momentum, while the Nesterov accelerated gradient (NAG) uses the projected gradients. Subsequently, the adaptive moment estimation (ADAM) computes adaptive learning rates for each parameter. In the presence of random disturbance, the state dynamics become fluctuate, and the entire state trajectory is uncertain. Without the complete state information, optimizing and controlling a dynamic system will not provide a satisfactory solution. In past studies, the KF method has been applied for estimation. However, it assumes that the system and observation model equations are both linear. This is not realistic in many real-life situations. The EKF method is a common approach used in nonlinear systems. However, linearization process is needed in deriving a filtering algorithm. Moreover, using the nonlinear filtering theory to estimate the state dynamics would be computationally demanding. Hence, an efficient computational algorithm is necessarily required. Therefore, the study aims to propose the iterative algorithm for state estimation and control law design, which called the stochastic approximation for state control (SA for SC) algorithm. This proposed algorithm only requires the initial value of the state error covariance matrix. Unlike the common filtering approach, needs to derive the equation of the state error covariance matrix. Moreover, the SFOSC algorithm will include the SA variance for handling the nonlinear stochastic optimal control problem, and their efficiency will be examined. There are three objectives of this study. First, to propose the SFOSC algorithm for estimating the state dynamics and designing the control law design to discrete time nonlinear stochastic optimal control problem. Secondly, is to compare the efficiency of the SFOSC algorithm with the EKF algorithm through mean squares of errors for solving discrete time nonlinear stochastic optimal control problems. Third, the objective is to verify the efficiency of the SA variance, namely SAM, NAG, and ADAM approaches in the SFOSC algorithm for solving discrete time nonlinear stochastic optimal control problems. Next, scope of study. In this study, the SA approach is applied and the recent variants of the SA approach are further investigated to carry out the state estimation and to design the optimal control law. The computational approach is called the SFOSC algorithm. Three engineering applications, which are the inverted pendulum-cart system, four-tank system, and the Duffing electrical oscillator model are illustrated. These problems are identified as discrete time nonlinear stochastic optimal control problems. Therefore, the efficiency of the SFOSC algorithm will be verified by solving this problem. The significance of study includes: first, an efficient commutation approach for solving the nonlinear stochastic optimal control problem is proposed, which is the SFOSC algorithm. Then, an improvement in the design of the control law through the SA approach is carried out. The illustrative examples of the stochastic optimal control problem in engineering applications are studied, where the efficiency of the SFOSC algorithm and its variance is proven. Next, continue with literature review. A dynamical system studies the long-term behavior of a system. Deterministic model is a series of equations which accurately describe how the system will evolve through time changes. No randomness is presented in the dynamic, and when given the same input, the output of a deterministic model is always the same. However, a stochastic model exhibits randomness and unpredictable behavior and can generate multiple responses to the same stimulus. A control system can be described as a system that controls other systems to achieve the desired outcome. A linear system obeys the concept of superposition, while a nonlinear system does not follow. Almost all systems are nonlinear in nature, and majority are more difficult to analyze than a linear system. State estimation is the technique of finding the internal state of an energy system by fusing a mathematical model with input and output data measurements. Common filtering theory is used for estimating unknown variables based on observations collected over time. It is used to reconstruct the value of the unobservable variables using temporal series of observable variables. It is frequently referred to as the most accurate linear system estimator. However, in the real world, the majority are nonlinear systems. Extended common filter is appropriate for nonlinear model problems and is performed by linearization. However, linearization can only be used for the existence of Jacobian matrix, which is time-consuming and error-prone task and might pose stability issues. Stochastic approximation approach, which is also known as the stochastic gradient descent, is an optimization approach that is used to reduce the value of the loss function of a predictive model. The momentum method is a technique for accelerating gradient descent. It involves adding a weight version of the prior update to the current gradient update. Nesterov accelerated gradient method can be conceived of as a correction to momentum to avoid the problem of overshooting the minima. It's allowing the search to slow down as it approaches the optimum point, reducing the possibility of missing or overshooting. The adaptive moment estimation speeds up the optimization process by reducing the number of function evaluations required to reach the optimum. According to the previous study, the methods of LQR, LQG, and LMI are used to control the nonlinear inverted pendulum system, and the estimation algorithms of EKF and UKF are utilized. Most of the control of the nonlinear inverted pendulum system is carried out after linearization. The nonlinear four-tank system is controlled by using the methods of model predictive controller and the grasshopper algorithm in literature. However, for a better outcome to the four-tank system, optimization techniques that are used for controlling the four-tank system to be explored more effectively. The backstepping control techniques and Laffoner function are usually used in controlling the Duffing electrical oscillator. However, the SA approach will be proposed to be applied in this study to investigate the outcome of control of the Duffing electrical oscillator. Next, we continue with methodology. The research framework is shown in the flow chart. For general problem formulation, in the presence of random disturbance, the process noise is added to the state sequence while the measurement noise is added to the output sequence. Both noises are the additive Gaussian white noise. The initial state is denoted as a random vector with the mean and state error covariance matrix is given. Here, the aim is to determine a set of control sequence such that the expected cost function is minimized over the dynamical system, where the cost function is the total of terminal cost function and the operating cost function. As summary, the problem is known as the discrete time nonlinear stochastic optimal control problem. Next, the SA approach is shown, where theta denotes the set of parameters to be estimated. A is the gain sequence and G is the stochastic gradient. For estimation of state, first consider the system mean propagation is given, which are the expected state sequence and the expected output sequence. Next, to find the optimal state estimate, the weight least square problem is introduced, which is a loss function in the form of the sum squares of the arrows. Then, by taking the first order derivative, the gradient of the sum squares of arrows is defined. On solving the weight least square problem, the SA approach is applied to calculate the optimal state estimate and the optimal output estimate is measured. For optimal control law design, the expected cost function is defined for which the cost function is measurable in its expectation. Then the Hamiltonian function is defined. A set of necessary conditions for solving the optimal control problem is derived, and the control variable should be chosen to optimize the Hamiltonian function. Thus, the augmented cost function form where the Hamiltonian function is used. Taking the first order derivative to the Hamiltonian function, the optimality conditions are derived, where the stationary conditions, state equations, co-state equations, Albert equations, and the boundary conditions are shown. An equivalent optimization problem is defined, where the necessary conditions of state equation and the co-state equation are satisfied. By virtue of this, the gradient of the objective function is expressed, where the gradient of the augmented cost function with respect to the control variable is the gradient of the Hamiltonian function with respect to the control variable. Hence, the updating equations based on the SA approach for the control law design are given. The computational procedure for applying the SA approach to state estimation and control law design is summarized as an iterative algorithm and is named the Stochastic Approximation for State Control SA4SC algorithm. The flowchart of the SA4SC algorithm is shown. The recent variants of the SA approach, which are the SAM, NAG, and ADAM, are also utilized in the SA4SC algorithm for solving the stochastic optimal control problem. The updating rules are given. The EKF algorithm that used as a benchmark to assess the effectiveness of the SA4SC algorithm is presented. First, the state mean propagation is considered. To find the optimal state estimate, the weight least squares problem is defined. Then, by taking the necessary condition, the optimal state estimate is obtained, where the common filter gain is shown as equation below. The state error covariance matrix equation and the output error covariance matrix equation are calculated as the equations show. The linearization of the dynamical system is done for the Jacobian matrix A and B. Then, the control law is designed as follows, with the common feedback gain and the Riccati equation as shown. Next, we continue with result and discussion. An inverted pendulum is a system where the mass center is above the pivot point. It was initially utilized in Great Britain in 1844 to design a seismometer. The stability issue of the inverted pendulum is the benchmark of a control system problem. A moving cart is used to move the pivot point of the inverted pendulum to generate a counter moment, which is called the inverted pendulum-cart system. The nature of the inverted pendulum-cart system is a single input and multi-output system with the control voltage as the input, while the cart position and the angle of the pivot are the output of the system. The inverted pendulum-cart system is highly unstable when the system is uncontrolled and it is a highly nonlinear system. In addition, in the presence of random disturbance, the task of controlling the movement of the pendulum-cart system becomes more challenging. The model formulation of the inverted pendulum-cart system is shown. The kinematic of the pendulum system is given, while the velocity of the pendulum system is presented. Then, the kinetic energy and the potential energy of the pendulum system are considered. The Lagrangian, which summarizes the dynamics of the entire system, is defined and the motion equation of the pendulum system is derived. The dynamics of motion is given, where the cart position dynamics and the pendulum angle dynamics are shown. Then, define the state variables and the control variable. Here, the state variables are the tilt angle, angular velocity of angle, cart position, and the velocity of cart position, while the control variable is the external force. The state equations of the inverted pendulum-cart system is formed, and its equivalent discrete time state equation is given, where the output variables is also defined where the output measurement channel is given. For illustration, those values for the parameters are shown. The simulation results of the SFOSC algorithm and the EKF algorithm are shown. It is devoted that the optimal cost of the SFOSC algorithm is 5.14% less than the optimal cost given by the EKF algorithm. This reduction proves that the practicality of the SFOSC algorithm in minimizing the cost function is superior to the EKF algorithm. The MSE value obtained by the SFOSC algorithm is 98.07%, smaller than the MSE value given by the EKF algorithm, which reveals that the optimal output solution provided by the SFOSC algorithm is very close to the real output solution. Therefore, the efficiency of the SFOSC algorithm is indeed higher than the EKF algorithm. Moreover, the MSE value obtained by the SFOSC algorithm is closing to zero, indicating that the random error component is small, and the estimated values are relatively accurate for prediction. Thus, the accuracy of the SFOSC algorithm is verified. The real and final output trajectories using SFOSC algorithm are shown in the figure. In the presence of random disturbance, the solution for tilt angle and the solution for the cart position fluctuate. However, by using the SFOSC algorithm, the optimal trajectories could be well estimated. The graphical results show that the tilt angle derived between negative 0.45 radian and 0.32 radian, while the cart position displaced between negative 1.66 meter and negative 0.71 meter. These figures show the real and final state trajectories using SFOSC algorithm. From the graphical result, these state trajectories have been estimated statistically. The angular velocity of the angle indicates that the tilt angle is moved with a decreasing rate and the cart position has a negative velocity that occurs in the period concerned. Therefore, in handling the inverted pendulum-cart system, these state estimates could be reliably produced using the SFOSC algorithm. The final control trajectory and the stationary conditions are shown in the figures. The optimal control of the external force is effective between negative 20 Newton and 14.3 Newton. The control effort is decreasing to zero to prove that the system is under control. Thus, the external force controls the tilt angle and the cart position of the inverted pendulum-cart system. The optimal solution is verified through the satisfaction of the stationary condition. The values of the gradients are between negative 0.022 and 0.014. The values are small, which support the satisfaction of the stationary condition. Thus, the optimal control, that is the external force, has been verified. Next, the simulation results for the variance of the SA approach are shown. The iteration numbers used by this algorithm to achieve convergence are different. From the result of these iteration numbers, the Adam approach shows 86.76% fewer than the iteration numbers of the SA approach and is 64.15% faster than the SAM approach. Moreover, it is 47.59% less than the NAG approach. Hence, the Adam approach uses the least iteration number to achieve convergence and shows a better guaranteed convergence rate. The figures show the convergence of state estimates and control sequence using the SFOSC algorithm with different variants. From the graphical results, all the SFOSC algorithm variants can achieve convergence with different iteration numbers. However, the Adam approach has a higher rate of convergence compared to SA, SAM, and NAG approaches because the gradient norm of using the Adam approach towards zero faster than other approaches during the iteration process. Next is the four-tank system. It is a multiple input and multiple output process, where the inputs to the process are the voltage to the pump, and the outputs from the process are the liquid level in the lower two tanks. The coupling effects between the inputs and output give the nonlinear behavior of the system. The goal of the system is to control the liquid level in the lower two tanks with two pumps. Additional flow disturbance can be added to the system, and this makes the control of the four-tank system become more challenging. The optimal control of the four-tank system gives significant economic benefits, as well as offer environmental and operational safety. For modern formulation of the four-tank system, The relations between the flows and the flow out of the tanks are given. Then, the mathematical model of the four-tank system is described, and the dynamics of the four-tank system is given. Define the state variable and the control variable. The state equations of the four-tank system is formed, and its equivalent discrete time state equation is given, where the output variable is also defined, where the output measurement channel is given. For illustration, the values for the parameters are shown. The simulation result for controlling the four-tank system is presented as in the table. The optimal cost of the SFOSC algorithm is 5.11% less than the optimal cost given by the EKF algorithm. Therefore, the practicality of the SFOSC algorithm in minimizing the cost function is presented based on this reduction. The MSE value obtained using the SFOSC algorithm is closing to zero and is 98.44% less than the EKF algorithm. Therefore, the result presented revealed that the accuracy of the SFOSC algorithm is verified and is indeed higher than the EKF algorithm. The real and final output trajectories of liquid level in tank 1 and tank 2 using the SFOSC algorithm are shown in the figures. The solution of the liquid level in tank 1 and tank 2 fluctuated in the presence of random disturbance. However, by using the SFOSC algorithm, the graphical results reveal that their optimal trajectories are well estimated. The liquid level in tank 1 was reduced from 10.2 cm to 4.5 cm, while the liquid level in tank 2 was dropped from 15.9 cm to 10.6 cm within the period concerned. By using the SFOSC algorithm, the state trajectories, which are disturbed by random noise, have been well estimated statistically. The graphical solution revealed that the liquid level in tank 1 and 2 are well predicted to the real liquid level, while the liquid level in tank 3 and 4 are smoothly predicted, which are not affected by the fluctuation. The figures show the final control trajectories of the input voltage to pump 1 and pump 2 using the SFOSC algorithm and the stationary conditions for the four-tank system. The control effort of the optimal input voltage to pump 1 and pump 2 are approaching zero, proving that the system is under control and tends to be stable. The optimal solutions are currently since the values of gradients for the input voltage to pump 1 and pump 2 are small and support the satisfaction of the stationary condition. Next, the simulation results for the variance of the SA approach are shown. The optimal cost given by the SA approach and the variance are almost the same. However, the iteration number used by each SA approach variance to reach convergence are different. From the result, the iteration number of the ADAM approach is 87.44% less than the iteration number of the SA approach and is 55.89% fewer than the SAM approach. Moreover, it is 45.43% less than the NAG approach. Hence, the ADAM approach shows a better assured convergence rate. The figures show the convergence of state estimate and control sequence using the SFOSC algorithm with different variance. From the graphical result, the SFOSC algorithm with variance reach convergence during the iteration process. It clearly shows that the ADAM approach has a better convergence rate than SA, SAM, and NAG approaches, as the curve of gradients norm using the ADAM approach tends to zero faster than the other approaches. The Duffing electrical oscillator model is an electrical circuit containing a nonlinear inductor. It can be presented mathematically in a second-order ordinary differential equation, namely the Duffing equation. The model exhibits chaotic behavior, which is disordered and unpredictable for the output of the circuit. Furthermore, in the presence of random noise, the electrical oscillator is more complex to be solved. For model formulation, the nonlinear inductor in the Duffing electrical oscillator can be modeled using the current flux nonlinear characteristic described by the following relation. Then, the relation for the voltage of the resistance, voltage of the inductor, and the current of the capacitors are given. The electrical law are also introduced. Substitute the relations into the electrical law to obtain the differential equations of the system. The differential equation is obtained as shown, and for simplicity, we note the variables and the Duffing electrical oscillator model is obtained. Then, define the state variable and the control variable. Here, the state variables are the flux through the nonlinear inductor and the voltage of inductor, where the control variable is the sinusoidal source. The state equations of the Duffing electrical oscillator is formed, and its equivalent discrete time state equation is given, while the output variable is also defined, where the output measurement channel is given. For illustration, those values for the parameters are shown. The optimal cost of SFOSC algorithm is 4.22% lower than the optimal cost of the EKF algorithm. This percentage shows that the cost function of the system is minimized by utilizing the SFOSC algorithm practically. Besides, the MSE value of the SFOSC algorithm is close to zero and is 99.98% less than the MSE value of the EKF algorithm. This small MSE value indicates that the optimal output solution can be estimated very close to the real output solution. Thus, it can be concluded that the SFOSC algorithm is more efficient than the EKF algorithm. The figures show the output trajectories of the flux over the nonlinear inductor and the voltage of the inductor using the SFOSC algorithm. The graphical results show that the final output trajectories are closely fitted to the real output trajectories. The optimal amount of the flux over the nonlinear inductor shall be maintained between negative 0.27 Weber and 1 Weber, where the optimal voltage of the inductor is controlled between negative 0.85 watt and 0.24 watt within the time constant. The state trajectories are shown in the figures. By using the SFOSC algorithm, the real state trajectories have been well estimated satisfactorily, where the flux over the nonlinear inductor is between negative 0.26 Weber and 1 Weber, where the voltage of the inductor is between negative 0.88 watt and 0.23 watt in the time constant. The final control trajectories and the stationary condition which is satisfied are shown. The optimal control of the time-dependent sinusoidal source is between negative 0.65 watt and 0.65 watt, varies as a sine wave with time. The control effort is decreased and close to zero, proving that the system is under control. Hence, only a little additional sinusoidal source is required when the circuit becomes stable. For stationary condition, the values of the gradient are small, which support the satisfaction of the stationary condition. Hence, the controller design using the SFOSC algorithm has been verified. Three SA approach variants are applied in the SFOSC algorithm and the simulation results are shown. It could be seen that the Adam approach ranks at the least iteration span, which is 20. The Adam approach shows 99.78% less than the iteration number of the SA approach, 99.18% faster than the SAM approach, and 98.66% less than the NAG approach. Hence, the Adam approach demonstrates a higher assured convergence rate for solving the problem. The convergence of the state estimates and the control sequence using the SFOSC algorithm are presented. From the graphical result, the Adam approach has a higher rate of convergence as the values of the gradient norm using the Adam approach tend to zero faster than the other approaches. Nonetheless, this SA approach variants achieve convergence successfully during the iteration procedure. Lastly, conclusion and recommendation. For contribution of study, first, the discrete time nonlinear stochastic optimal control problem is formulated, where the existence of random disturbance in the system is considered. This makes the problem more complicated, but closer to the real condition in engineering applications. Next, the formulation of the SFOSC algorithm is demonstrated, where the calculation procedure is simplified. In addition, the optimal trajectories of the stochastic optimal control problem are obtained by carrying out the state estimation and the control law design. The practicality of the SFOSC algorithm is verified, where the simulation results prove that the SFOSC algorithm outperforms the EKF algorithm in terms of optimal cost, and the efficiency of the SFOSC algorithm is guaranteed. Among the SA approach variants, the Adam approach shows a better guaranteed convergence rate for solving the nonlinear stochastic optimal control problem. The limitation of the study is to determine the appropriate learning rate for each model. In the SFOSC algorithm, the learning rate is important in the updating rule. It affects the speed at which the model solution converges to the optimal solution. Choosing a suitable learning rate is challenging. Typically, the users configure the learning rate randomly or use the prior experience to determine the best value for setting the learning rate. Here are some recommendations for solving the optimal control problems in the future study. First, determine a learning rate that is suitably used for each application. Next, use different variants of the SA approach to improve the performance of the SFOSC algorithm for attaining a better convergence. In addition, explore more engineering applications to be handled with the algorithm proposed. That's all from me. Thanks.